So multiple dimensions is really a slight extension of the finite volume scheme on a non-uniform grid. So in multiple dimensions, let's write our conservation law as partial u partial t plus the divergence of a flux vector, which is a function of the solution u equal to 0. Okay, and let's actually make a little bit more general form. Why can't I erase that? Okay, is equal to a function g, let's say, which can also be a function of u. So g is called the source term, that is the non-conservative part of the equation. So in momentum conservation, for example, g can be a body force, gravity, for example. In conservation of energy, g can be a source of energy coming from something else. Let's say if you are so in fluid dynamics equations, g comes from chemical reaction, right? So these are, g is a source term.
So u is a scalar.
Huh?
U is a scalar.
U is a scalar. Yeah, g is also a scalar. F is a vector corresponding to 2 or 3 dimensions, depending on how many spatial dimensions we have.
The gradient dot f. So gradient is what? Like,
so the gradient is, no, this is the divergence. This is not the gradient. So f as a vector of u, I can write it as fx of u, fy of u, fz of u. These are different components, x, y, z components of the vector. And the divergence of this vector u is defined as the partial derivative of fx to x plus partial derivative of fy to y plus partial derivative of fz to z. If you apply the chain rule, because f is a function of u and u is a function of x, y, and z. If you apply the chain rule, you're going to get partial fx. This is no longer partial because fx is a function of u in this case. dfx du times partial u partial x plus dfy du times partial u partial y plus dfz du partial u partial z, right? And this can be written as df vector du dot with the gradient of u, where the gradient of u without the dot is defined as partial u partial x, partial u partial y, and partial u partial z, right? So depending on if you write the second term as the divergence of a flux or equal to a vector field df du dot with the gradient of the solution. This is 2 different differential forms of the same equation. This is the conservative form. This is what form? The primitive form of the equation. Okay. So the first step in deriving finite volume is to take the conservative form of the equation and integrate to get the integral form. Right? So we take, this is the conservative form, and this is the primitive. We take the conservative form of the equation, we integrate. Integrate over space, over a finite volume. What we get is integration over a small volume, let's say over v, partial u, partial t, plus divergence of f of u is going to be equal to integration over the same v G of U, dV, let's say dV. And the first term, because V is a constant volume, right? In our setup, V is a constant volume. If V actually changes as a function of time, then there are more terms that is coming out. But right now, let's say we have a fixed volume, we have a fixed mesh, and each cell, each finite volume is a stationary, it's stationary in time. What we get is d dt of the volume integrated, U integrate over the volume, plus, and we apply the divergence theorem. Integral of the divergence of a vector is equal to integral over the boundary, right? So the Nabla operator is exchanged, is replaced by the normal, the outward phase normal at the boundary. Dot with the same f of u, dv becomes ds. And this is equal to integration of g dv. Okay, and in finite volume, we track something that is closely related to the cell integrals, which is the cell averages. So we divide both sides by the volume of the cell, by the volume of V. Let's just call it V. Right, so this is the volume of the cell. And again, if V is stationary, if the mesh is stationary as a function of time, we can take the V into the time derivative. So in the finite volume, so let's say if I have a cell and I discretize, if I have a space where I want the solution, if I divide the space into V1, V2, V3, V4, V5, V6, V7, etc., then the d dt of ui, where ui is defined as 1 over vi, the cell size, times the 1 over vi times the cell integral, this plus 1 over vi integrated over the boundary of vi. So for v1, the boundary is like this. For v2, the boundary is like this. For v3, the boundary is like this. Okay. The surface normal dot with the flux vector ds is equal to gi, which is the cell average of G computed on the ith volume. So up to now, this is still exact. And now we start the approximation. So this is still exact. The approximation is the following. We are going to approximate two things. We're going to approximate, first of all, this integral over the boundary of a cell. We're going to approximate the boundary as a piecewise constant. We are going to approximate this f as a piecewise constant function. So for example, let's take V2 as an example. V2 has one part of boundary interfacing with V1. It has one part of the boundary interfacing with V3, one part interfacing with V4, and one part interfacing with V5. And we can split up this integral over the entire boundary of Vi into a summation of integrals. And the summation is over all the cells, all the boundaries that are over all the cells that are neighbor of that particular I. So I'm going to write it as J inside the neighbor MBR of I. J is defined as a neighbor of I if I and J shares a non-trivial interface, right? So if the flow can, if the flow can go from cell I to cell J through a boundary, and this is the phase normal between I and J. So this is the average phase normal between I and J, dot with the flux between I and J, and ds is going to be S I and J. Okay, this normal is the average, the normal of the interface. S is the total amount of interface length. In particular, this approximation is approximating this f as piecewise constant, right? So, and if we do that, we can say that the integration over partial, over the boundary of I and J of n ds is going to be defined as nij, which is a unit vector, times sij, which is a scalar. Okay, so if we say f of u is a constant over the interface, we can pull that f out of the integral, and the integral is a purely geometric quantity. The integral of phase normal times ds. Now if you work it out, this is a vector. This is a vector that is connecting the whole interface. The length of the vector is the distance between this point and this point, is the distance between one side of the boundary and the other side of the boundary. And the phase normal is exactly orthogonal to the line connecting these 2 points. Okay.
Why
Right.
the line as in if it is multi-dimensional, it can be a plane, right?
Oh, that's a very good point. I'm thinking in 2 dimensions. If you have multiple dimensions, yes, it's a plane. It's not just a line. So you will be integrating the phase normal over a potentially a non-trivial surface, and the magnitude of that integral is going to be Sij. The direction of that integral is going to be your Nij. One of the trivial cases is when, let me go to the mesh then. So this plus this is equal to, if we also approximate Gi as piecewise constant, then we are going to be applying G onto Ui. The function G applied into Ui is going to be my right hand side. So here, if I can approximate the piecewise constant surface flux, if I can approximate Fij as a numerical flux that is computed from Ui and Uj, then my finite volume scheme works. Right, question so far? We've been working through the same type of derivation as we derived in 1D. Except for now, we have a flux not just between the ith cell and I plus 1th cell, but in between any pairs of neighboring cells. And we are approximating the flux in between these neighboring pair of cells using the cell averages on these 2 cells. Yes?
What do you mean by a non-trivial boundary?
A non-trivial boundary is a boundary that has length more than 0.
So it's not a point.
It's not a point, yes. Yes. So for example, if you have a grid like that, this and this are neighbors, but this and this are not called neighbors. All right.